Hello and welcome back to Calculus 3, the last section of chapter 13, 13.7 on change of variables in multiple integrals. So, you made it to Calc 3, which means that you are good with U sub. Otherwise, you would never make it this far. Do I need to switch? Is there something I should know?
That's terrible.
Let's make it worse now.
Oh, yeah.
So what we are going to do first is look at the U sub and actually understand what is happening. So we'll do some kind of easy problem. Let's say we have x cosine x squared dx, right, from negative, let's not negative, let's go from pi over 6 to pi over 3, okay? So this is the integral we have. Now we are looking at this, and the only way we can solve this is to use U sub from Calc 1. Now, what is happening? Please understand here that you are looking for area under the curve, which is given by this function, and the function is in terms of x. So whatever the graph for this function is, and I'm just going to draw whatever. Whatever the graph is, let's say this is the graph, we are looking for this area. Note that your domain x, right? Domain, the input is x. And we are looking for this area here. Now, what I'm going to do is, because it's a bit annoying to do this, we are going to use U sub, which is actually change of a variable. So now my, you know what, I'm actually going to look up the exact function for this. So let's go with Wolfram alpha, there we go, graph x cosine x squared. All right, so it is one of these squiggles. So x cosine x squared would actually look like this. So this is what it looks like on the screen, right? And they say that this is around 2, so our interval is in here. So here is a bump. Okay, so now we are going to deal with, because I can't integrate this. Luckily, we know U sub, right? And write that U is equal to x squared. So du becomes 2x dx. That's technically the differential. And we realize that we don't have this 2, so I put in a 2.5 in front to balance it out. And now we get to 1/2 integral. 2x dx is du. And then we have a cosine of u. Now, what I'm going to do is I'm going to transform limits as well. Because if you think about this, your limits are x, your variable is x, and the integral is dx. So everything on this integral is x, which means that once I switch the variable from x to u, everything has to be u. Well, we at least see that the function is in terms of u, and we have du. So now we also have to make sure that the limits on the integral are also u. Now that's very easy because we have an equation that connects these things. So my u in the denominator is going to be pi over 6 squared. And pi over 3 squared on top. So we just plug each one of these into the U sub we have and compute. Right. So now I have to integrate. So I have 1/2, and then the integral of cosine u is sine u, and that's going to be computed from pi over 6 squared to pi over 3 squared. So, as you can see, we transformed the integral, but we also transformed the limits. Now, if you are to do the change of variables in double integrals, you are not only transforming, right? By transforming limits, we mean you are transforming the region. And that is the part that you have never done before. So we have to learn how to transform the region. Then you have to transform the integral. Then you have to transform the differential. And then finally, you can do the problem. So this is going to have like 4 components. And 2 of those components you haven't seen before. So let's go. First, we are going to learn how to transform a region. So we are going to have some kind of transformation function which will take a region in, let's say, xy and transform it into region uv. Now, we are going to have a transformation function that actually does that transformation. And there is a lot of application for this. Actually, computer science could benefit on this one. The transformation is the part that transforms one type of array into a different type of array. So that's something else. All right, so now let's take a look at transforming a region. I just need a region first that we are going to transform. There are some regions that are transformed in a textbook as an example. You can read those. I'm just going to go with one of the homework regions to transform. So, good. So guys, here's what's happening now. To transform a region, we are going to have some kind of region in xy domain. So we have some kind of region here. I just draw the yeah, the word is just gone out of my head. I think it deleted. General, there we go. We have some general region R, and then we are going to use the transformation T, where x is equal to some function of u and v, and y is equal to some different function g of u and v. So when we have that happen, you are going to get some kind of a different region. There we go. We're gonna call that region S, and that region S is going to be in the UV domain. So it's important to, so I just drew whatever general regions that are different than each other, right? To emphasize this. So what you can get a triangle that transforms into a circle that transforms into a square, a parallelogram that transforms into a square. You can get anything, right? It's important to follow the transformation, and then the mathematics will take you from one shape to another shape as you graph. So let's see some of the transformations here. Okay, this is a backwards transformation, but still it works the same way. So they're giving you a unit square to begin with. So I have a unit square. 0, 1, 1, 1, 1. There we go. And this unit square in S can be understood as all the points UV such that U is between 0 and 1 and V is in between 0 and 1. So that's what I have. Now I want to use transformation T. Let me see what they give. Pick, I guess, any one of these. So let's go with problem 6. That's easy. T transformation is x equals negative u, and y is equal to negative v. So this is what you generally get. You know what your region for integration is, right? And that's going to be your input region. And then you either discovered it on your own or you are given the transformation, which is technically you are picking your u for u sub. And then you transform the region in the manner I'm going to show you now. What I'm going to do is I'm going to break my square up there into 4 lines, label them as 1, 2, 3, and 4. And I'm going to work on each one of those regions one at a time. So, region number 1, line number 1. First, I'm going to describe this line using mathematical formulas, and then I can do substitutions. So this line is described by 2 equations. One equation is clearly that x is equal to 1 at all times. So x equals 1, and that's actually a vertical line. But see, the problem with this x equals 1 is that it's not bounded. So this x equals to 1 goes forever up and forever down. Never stops. Which is the reason why I have to have one more equation to describe this. And that equation says that y is trapped between 0 and 1. So these 2 equations together, the equation and the constraint, give us the line segment between 0 and 1 that it's going vertically at x equals to 1. So now I want to transform this. Well, how do I transform it? It's as simple as substituting values, right, that you have. Now, hold on, this is backwards, because the domain over here is u and v. So these are u and v. There we go. Sorry about that. The problem is given as u and v over there, and we are transforming it back into our xy domain now. So what do I have? I have x-axis, which is now u-axis, and we have a v-axis. And if I want to describe this line segment here, that is going to be on the equation u equals 1, cut off at 0 and cut off at 1. So here is the infinite line, and this is the cutoff to give us that little segment that we are looking for. Now, the only thing I need to do is to plug in transformation and replace all u's and v's with x's and y's. So in the first equation, I'm going to, instead of u, put negative x equals 1, from where I come up with a new equation, x equals negative 1. Then I'm going to replace a v with negative y. So I have 0 less equal than negative y less equal than 1. Now, we need a y in the middle to be positive y, so we have to divide everywhere by negative 1. What happens with signs? The signs changed, yes. So now divide by -1, divide by -1, divide by -1. So we are going to have 0 larger than y, larger or equal than -1. So now I'm just going to bring that here and say that x is equal to -1 and y is in between -1 and 0. I'm going to box this slightly or circle it because this is actually transformation of my first line. Yay, 3 to go. Line segment number 2. Line segment number 2 is the horizontal piece on top of the square, whose equation is v equals to 1, and u is stuck between 0 and 1. So now we do the same transformation. We replace v with -y, and then we finally get that y is -1. Next, we have to deal with the region, and the region is from 0 to 1. Again, we substitute instead of u -x, so 0 less than -x less than 1. And now you divide everywhere by -1 to get 0 larger than, so I'll write here divide by -1. So now you know that you have to switch the signs. X and then larger or equal than -1. So bring that thing there and have that, oh, one more step. -1 less equal than x less equal than 0. There we go, much better. So bring this forward, and now what do I have? I have y is equal to -1, and I have that x is stuck between -1 and 0. So I'm going to circle this lightly because that is my second line transformation. Third part of this diagram, as you can see, number 3, is going along what used to be y-axis. Now it's v-axis. So it sits on the equation u equals 0 because that's the axis for it. So we are going to have over here u equals to 0. So that is our v-axis. And then the v is stuck between 0 and 1. Again, replace the transformation in. So we have -x equal to 0. Well, that's just x equals 0. That doesn't change. And on the other side, we have the change because we have 0 less than equal than -y less than equal than 1. Then we divide by -1, we get 0, switch the sign, so larger than now y, larger than -1. So we have that -1 less equal than y less equal than 0 is the transformation for the third part. This is all fun and games when I'm doing it. When you try, you'll have to, you know, pull some airs out first because it's going to be not that simple. The last one is v equals 0. And u is between 0 and 1. So now v equals to 0, we plug in y, so y equals to 0, great. And over here we have 0 less than -x less than equal to 1, divide by -1, and we get -1 less equal than x less equal than 0. So that goes easy, easy. That goes here. And these two are now a pair. All right, so let's draw the new region, the transformed region. So now my coordinates are x and y because all of my equations are x and y. So transformation helped us eliminate all of the u and v variables and left us only with x and y variables, which is what we can deal with. Now, let's go and plot the point, draw these segments. So x equals -1 from -1 to 0. X equals -1 from -1 to 0. There you go. So this one over here is the stage 1. So now, the next one is number 2. We have y equals -1. Y equals -1 is this, and then they want also from -1 to 0. So this is number 2. Then number 3, x equals 0, and y is from -1. So that will be this piece, x equals to 0. So that will be this. So that will be piece 3 and piece 4. We just changed the location of the square with this transformation. Now, it's a very good exercise because look what happened. Please look at the place where the old square was. This is the place where the old square was. And look at your transformation. Transformation says that your x, or no, your u should be -x and your v should be -y. Well, isn't that exactly what we did? Every x, right, became, or every u became -x. So we just went from having all of the points over here to be positive, comma positive, to be negative, comma negative. Because that's the third quadrant, both coordinates are negative. All right, let's take a look at the spicier transformation. This is very long. These problems, and guys, you know what this is doing? This is just working on the limits of the integrals. We haven't touched yet the inside that has, you know, things. So, yeah, we'll be doing this tomorrow still. All right, so let's go. I just want to transform. I'm not solving the problem. I'm just going to say transformation from problem 28. I'm not solving problem 28 now. I just want to use the specs. So the region R is given by all of the points x, y, such that x is between 0 and 2, and y is in between x and x plus 4. Use transformation x equals 2u, y equals 4v plus 2u. All right, the first order of business is to draw the region R, because we need to do the numbers, right? So let's get busy. X is in between 0 and 2. So technically, if I am to draw anything for that, I will put the bounds at 0 and 2. So these are the lines that I will later erase. So let's say this is one, 2, 3, good effort, 4. It happens all the time. People become delusional in this lecture.
I don't think that was delusional. I think it was hysterical.
Yeah. So now, guys, please note that I have two equations here that you know how to graph. What is the y equal x line? Yes, it's the 45-degree line. And as you can see, we are not crossing 2 because the diagram stops there. So domain tells us that we have a vertical asymptote at 2. So now I use the other side, which is the other equation. And that's y equals x plus 4. Well, I need 1, 2, 3, 4. Oh, come on. The scale is off, yeah, which means that I have to use my divine powers over here too. Like this. It's in the equation. You see how I circle it? That's given to you. So 1, 2, 3, 4, and it's a 45-degree angle again until it reaches the.
Wait, so the other one is from 0 to 2?
That's what the two green lines are for.
And this is x.
So this is x being between 0 and 2.
So what are those lines going to?
Well, hold on. I have to connect everything now. So we have parallelogram. Your input region R is a parallelogram, and yeah, they're not too fun to compute integrals off of them. So what we are going to do is we are going to transform this region now into something that hopefully we can work with. And we have our transformation. So let's label the parts. Part 1, part 2, part 3, part 4. Part 1. First I have to describe the equation, and then I get to do the chopping and stuff. Yes.
Does it matter which part?
What do you mean?
Like, does that have to be in a certain order? Like, could one be a diagonal line?
You've gone like.
Like, one on the top, two on the side.
No, the problem clearly says that x is between 0 and 2. You can't change that.
No, what I'm asking is, like you have your order. You have your 1, 2, 3, 4. Right?
Oh, you can put them in any order.
Oh, okay.
Yeah, you can start your number 1 over here and then go clockwise if that makes you smile on Wednesdays. What are we having? All right. Number 1. Let's go and describe this. Clearly, it's on equation x equals to 2. And now I need bounds. Bounds are from the correctly drawn diagram, which I actually don't have. It's going to be 2. Supposed to be 2 to 6. Did I miss?
Yeah.
Oh, I missed the tick marks. There we go. So y is stuck between 2 and 6. Then we have line number 2. Line number 2. This is line number 2. Well, I don't actually have to work hard to figure out this equation because this equation is already given to me. It's right here. y equals x plus 4. Line 3 to transform. Line 3 is going to be x equals 0. Yeah.
You don't need a boundary for 2.
Oh, yeah, I do. Bounds are 0 to 2. Yes. Okay, so number 3, x is 0 and y is stuck between which values, guys? 0 and 4, thank you, yes.
What is that?
It's math.
No, like number 2.
Isn't it X?
Why is it like this?
Yeah, that's where we're at.
Okay, is it better?
Yeah, there you go.
Yeah, there I go. And the last one is y equals x, also on 0 less than x less than 2. So what I have here are just the descriptions for each of the 4 lines, and now I go and I use the transformation, right? So region 1, which is given as x equals 2 and y being between 2 and 6, we are using transformation where where x is equal to 2u and y is equal to 4v plus 2u. To do this transformation, we simply replace x with 2u and y with the rest and see what happens. So x is no longer there. Now it's 2u equals to 2. Okay, so u is equal to 1. Over here, for y, I have to plug in the whole thing from the substitution. So we have 2 less equal than, and instead of y, I have 4v plus 2u.
Now, did you plug in 1 for u in that?
Yes! Nice.
Weird.
What happened?
Me too. Oh my god. Yeah.
What?
Yeah. Oh my god. Yeah.
But better?
Yeah.
I got this. Don't worry, I got this. So 4v is plus 2 because 2 times 1 less than 6. What happened to what?
Never mind. I'm substituted in. I'm sorry.
That's okay. So now subtract 2 on all 3 sides. So 0 less than 4v less than 3. No,
What?
4.
What? Oh.
I subtracted 2. I need to fish out v. And then I divide by 4 everywhere. So 0 less equal than v less equal than 1. Yes!
Uh-oh.
That is the first. Guys, we are 75% into the 10% of the problem. Nice.
Why would you say it?
We are 25% into the 10% of the problem. Good.
2.5%. Just say that. Say that. Break it to us. It's fine.
Region number 2.
Would you be able to plug in like u from number 1 into number 2?
No,
Okay.
they're all disconnected.
Okay.
Y equals x plus 4. And we have between 0 and 2. All right, so we have the same drill. We have our functions, and now it's time for us to transform this. Every y gets plugged in, every x gets plugged in. So what I have is that x is 2. So y is 4v plus 2u equals to x is 2u plus 4. From here, 4v is equal to 4, and v is equal to 1. Plus minus 1. No, it's just 1. I was just testing you. And you passed. When we transform the other side, we get 0 less than 2u less equal than 2. And 0 less equal than u less equal than 1. Yep. Maybe I should be circling these. There you go. All right. Number 3. Region number 3 is x equals 0 and y is from 0 to 4. X equals 0 and y is trapped between 0 and 4. So we use our transformation where x is equal to 2y. So I mean 2u. So 2u equals to 0. U equals to 0. For the second part over here, we are going to take okay, so y, there we go. All right, so 0 less equal than y is 4v plus 2u. Less equal than 4, right? Okay. So now what we're going to do, we are going to plug in 0. So 0 4v plus 2u less equal than 4. Good.
Zero. Do the whole arrow and everything. And then do the same thing.
Oh, I meant to plug in 0, so this term dies. There we go. For the moment, I was like, what happened here? So now we divide everywhere by 4. Then we get 0 less than v less than 1. Yay.
Will you always get a v and a u alone in that inequality, or will sometimes stuff not cancel out?
Yeah, sometimes, most of the time, it doesn't cancel out. Region 4, y equals x and x between 0 and 2. X between 0 and 2. No yawning. For another 30 minutes. Another 30 minutes, no yawning. Or sniffling. Yes?
I've been looking for you my whole life.
I'm scrolling through all the responses and none of them are suitable at the moment. So we have y. to transform, that's going to be 4v plus 2u equals to x, which is 2u. So we have that 4v is equal to 0, v equals to 0. To transform the other one, 0 less than 2u less or equal than 2. Divide everywhere by 2, and we get 0 less equal than u less or equal than 1. And this is the final shape.
Wait, Professor, it's only when you divide by length that the sign switch?
Yes.
Oh, you can't even call one. You don't know your units. Oh, what'd you get, Calculus?
Ooh, shots in the fire.
I just had to, I just left that. I wanted to hear the whole thing, and I did. Thank you. All right, time to draw our new region. Let's be efficient, try to draw this before it dies. U equals 1 is a vertical line between 0 and 1. There.
Whoa. So U is like the x-axis.
Yes. Then the region number 2, part of the region, right, number 2, V equals 1, that's horizontal line that fits there. There we go, perfect. And then V is between 0 and 1, and U is 0. So that's this one. And finally, we have the one on the bottom. We went from, look at this one. We went from parallelogram into a very easy basic unit square. So now as you are setting up the integral for mass or whatever, you will say, oh, okay, 0 to 1, 0 to 1, it's your rectangular coordinates, you know them very well. So 0 to 1, 0 to 1, and then you do whatever you're supposed to do. Those are region transformations. Probably we can find more. Maybe there is a polar transformation somewhere. What is the conversion between x and a polar? X equals r cosine theta. Thank you. Or x. All right, good. Are you ready for 2D formula for change of variables?
No.
Great, because it's coming right up. Sharpen your pencils. Let's go. Double integral over region R for some integral fxy dA that you cannot compute in any other way other than changing variables is going to be equal to the double integral over the new transformed region S of f of g of uv comma h of uv times the Jacobian matrix in terms of the determinant of Jacobian matrix uv and then dA at the end. This is your integral. Now, it's a little bit busy, but we got this. I'm not in my room. I don't have my pointer.
Are we going to have to do these in 3D as well?
Do what?
Are we going to have to do these in 3D as well.
Yes, it's coming up. If you are patient. Please look at all of the guys. Look at all of the components that we have in this integral. Look. The part that we did so far is the transformation of the limits of integration, which transforms region R into region S. And those are the two problems we did so far. Then you have to take the function as is and change every x and every y of that function into u's and v's according to the transformation, and that goes here. Then you need to create a Jacobian matrix, which is a matrix of all partial derivatives, and compute the determinant of that matrix, which might be a number or might be a function which goes there. Then you unleash algebra to simplify this as much as possible, and at that point you should be able to integrate. So this is what U sub looks like in 2D. Obviously in 3D, far worse, right? So let's take a look at the problem now. I am going back and I'm going to continue problem 28, which we started here with transforming the region. So this was just a transformation of problem 28. I'm going to put a band-aid on that thing. So now I'm going to continue. Problem 28. So what do I have now? The problem 28, I only did the transformation of region. Now I need to pick up the rest of the problem so that we can go on computing this wonderful thing. We are supposed to compute the integral over a region R that is x squared y dA. So that's what we are supposed to compute. X squared dA. From problem 28. No, because I didn't need that. I only needed its region to transform it into S, because that was the part that we were learning. Now I want to do the rest of the formula, so now I need this piece. Okay. All right, so let's go with the transformation. I already know that my new region is that square 0 to 1, 0 to 1. So double integral 0 to 1 and 0 to 1 is going to be what we have. Now I told you that whatever, not talk my name in vain. Let's go. We have the x squared and the y. They have to be transformed into u's and v's, and I'm using the transformation. So transformation for x was 2u. So I'm going to transform x squared into 2u squared. And then transformation for y was that long thing with addition. 4v plus 2u. So 4v plus 2u. And this is transformation of the transformation of the function inside. So technically what I did is this part of the formula here, where I wrote the old function f, which was in terms of x and y. I wrote that function f now in terms of u and v, using the transformation, obviously. The next order of business is to compute the Jacobian. Jacobian J of uv is the determinant of the matrix of all partial derivatives. So, partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. This is again one of the necessary and important components. So now I am going to, I know what my transformations are. My x is equal to 2u, and my y is equal to, there was a 4v plus 2u. So if I'm looking for the Jacobian of u and v, partial derivative of x in respect to u is 2. Partial derivative of x in respect to v is 0. Partial derivative in respect to of y in respect to u is 2. And then finally, partial derivative of y in respect to v is 4. Solve the determinant. We all know what to do. So 2 times 4 is 8, minus 0 is 8. So that goes here, 8. That's the Jacobian. And then we have dy dx. Sorry, the dv du. Those are the partial derivatives, yes. It's a matrix of partial derivatives. Where were you? Oh.
Yeah.
Okay, solve. So we're continuing solving the integral here. What do I have? Well, first we are going to simplify the integral. 0, 1, 0, 1. What do I have? 2 squared is 4 times 8 is 32, and factor out 2, 64 in front of the integral.
And then does it matter what order you do it?
Yes, it does. But because we had a square, it doesn't. Right? Because technically, what you're going to put depends on the picture you have, whether it's going to be general region or the rectangular region or the polar region.
Why'd you take up 60?
Okay, well, let's see. 2 squared is 4. I factored out 2 from here, and I have 8. 8 times 2, 2 times 4 is 8 times 8, 64. Now what's left? What's left is u squared times 2v. U squared times 2v. And then 2 is out, it's plus u cubed. dv du. So this will be 2u squared v. To write it nicely. All right, so we go 64 integral 0 to 1. And now we are integrating in respect to v, so it's going to be v squared over 2. Over 2 kills the 2, so all I have is u squared v squared. Plus u cubed as a constant, we are picking up v. And those v's need to integrate from 0 to 1. And we still have du to worry about later. So now 64. And plugging into v, we get u squared minus u cubed. And 0 is going to kill everything. And we have du. So now when you integrate this, it's just, where? Exactly. Clearly says plus. Y is in minus. What do you mean y is in minus? So now I have, I started there. 64, and now I integrate, which is u cubed over 3 plus u to the 4th over 4. And what else? Computed from 0 to 1. Nice. So all of these are in terms of u. Okay, I have 64. Plug in 1, that's 1/3 plus 1/4. Now 1/3 plus 1/4 is clearly 7/12. So 64 times 7/12. These guys will cancel. I can cancel 2. No, I can cancel 4. So 20. No, 4 into. So 4 into 6 goes once, and then that's 8. Oh, that's the whole thing? 1/12/3. Okay, great. Ta-da, done. There's the value of the integral. Yeah, we kind of did start this problem yesterday, and then, you know. This is one full problem when it's not the trivial. Yes. So it takes a bit to transform the region. Once you have the region, you transform the integral, you make the Jacobian, and then after you have the Jacobian could be either a number or a function. That goes into the soup as well, and then you just integrate with whatever. All right, so now by popular demand, right, 3D. So we're going to write the formula. Everything remains the same. We can start with the Jacobian of UV.
Wait, that was 2D right there?
I'm pretty sure.
Partial derivatives. Partial x, partial u, partial x, partial v, partial.
So do we just assume u, v, and w go across and then x?
Yes.
Why do you go down?
Mm-hmm. Partial x, partial w, partial y, partial u, partial x, partial y, partial v, partial y, partial w. Nice. And then partial z, partial u, partial z, partial v, partial z, partial w. There we go.
And we have to do cofactor expansion.
Yes! This is the long expansion from. I know, but you do it with functions now.
Would we do it the same way in higher? As in linear?
4 by 4 would give you
So you do the
4 3 by 3s, and then each 3 by 3 gives you.
Okay.
Yes.
I thought I'd escaped this in linear. I'm really a little disappointed.
You so haven't. All right, this is the quick definition for the Jacobian that you will have to use. And now let's go and define the integral. So the triple integral over region D of the function x, y, z, dv, it's going to be transformed into a triple integral over the region S, f of g of u, v, w, h of u, v, w, and p of u, v, w, running out the letters.
Why H, G, H? Why? What logical sense does that make?
Just roll with it. Times the Jacobian of u, v, w, and then dv. There it is. Now, guys, this is GHP. Those are the transformations. So your transformation for here is that x is equal f of UVW, that y is g of UVW, and that z is p of UVW. You see, you can have a lot of fun with the expression like this. You can just go on random places and just write it and leave it behind.
Why would we leave it?
And no one would pay any attention.
You go to the restaurant, you write it on a napkin and leave it behind. Right?
That's such a power move. I'm kind of into it.
So what do we have?
I think it's good.
I don't know.
Sir.
We have the function that is now, with the transformation, shifted into UVW domain times dv. Right. It's a dot product. And then what order you're going to have for dv? Well, that depends on what the problem says. Right? The problem says that you have, that you have that. So these types of problems will take about an hour to do, because you have to transform the third-dimensional region, which might be a box with 6 sides.
So are we going to have to do that then on the final?
You know, like, is the final game like 2 of
We
these
should have enough
problems?
time for it.
2 of these problems?
Oh, you said, oh, sorry, 3 of them. Sorry.
There we go. See? Now you have the idea. So, yeah, that's 13.7. So we'll do one more problem tomorrow for good measure.
Oh.
Right? But you should practice. The homework is open.